Welcome back. In the last class, we proved this theorem in the last couple of classes, which characterizes when a given complex number is solvable over a given field. Okay, so there are three equivalent conditions that I wrote, and in fact, I forgot a fourth one, which I will write now because this will also be useful for us as we go forward. And this is a very trivial modification from the third one. So there exists a tower of fields, just like in the previous three cases. So let me call this M0, M1, MS, such that alpha is in MS, of course, and alpha is in the last one. Each Mi mod Mi minus 1 is not only cyclic, but it is cyclic of prime order. Okay, is this cyclic, meaning it is Galois. So Galois plus Galois group is cyclic, and moreover plus the index is a prime number. Of course, it is cyclic is now irrelevant here, because if it is of prime order, it is obviously going to be cyclic. But and the proof actually only proves 1, 2, 3 are equivalent. So I leave this as an exercise for you for now to show, for example, that 3 implies 4. This is an easy exercise. So basically, all you need to do is, if f this is a cyclic extension, implies there is a tower where each is cyclic, where each is prime order. This is easy, but I wanted to record it in the theorem itself so that we can just appeal to this theorem later. Okay, so obviously 4 implies 3 is trivial, because if there is a tower where each extension is cyclic of prime order, it is of course cyclic. But 3 implies 4, you can do by first taking a cyclic extension. Take take a subgroup of prime index. You know that such a thing exists, because if P divides the order of the group, there exists a subgroup of index P, right? That means order of H is order of G divided by P. Then you take the fixed field of that. That would be here. Okay, this is order P because that's the index, and then this has order, this is index is less than k colon f, and you proceed by induction. Okay, so this is just a hint. So any cyclic extension can be expanded by putting more fields in the middle and ensure that each extension is of prime order. Okay, so I just don't want to say anything more, but the conclusion of the theorem is that it is enough to consider a tower of cyclic extensions of prime order, and 2, 3, 4 are all Galois theoretic statements. The first one is solvability by radical statement. Now let's proceed. Our goal in the rest of the course is to prove. Okay, so what is our goal? So our goal now for the rest of the course, okay, is as follows. So I'm going to fix this notation once and for all. So f is a subfield of C. Okay, so I'm going to stick to characteristic 0, and in fact I'm going to stick to subfields of C. And we take polynomials in one variable over this field f. So we'll first show that n equal to 4, then f is solvable. Okay, so let me write that here. So f is a polynomial and n is the degree of f. Okay, so what is the meaning of solvability? It means all roots of f. So solvable, maybe I should write over capital F. So this means all roots of capital F are solvable all roots of small f are solvable over capital F. So if the degree of the polynomial is less than or equal to 4, all roots are solvable. And if n is greater than or equal to 4, in general, f is not solvable. So these are the two theorems that we want to prove. Of course, the word in general is important here. So let me remark here that there do exist polynomials of any degree that are solvable. Okay, I am not saying that every polynomial of degree 5 is not solvable. I am only saying that there do exist. So for example, if you take the polynomial x power n minus 1, by the very nature of the roots, these are all nth roots of unity, this is solvable for all n. So you can always construct polynomials which are solvable, but for n at least 5, there do exist polynomials which are not solvable. Okay, and however for n equal to 1, 2, 3, 4, all polynomials are solvable. Okay, so we are going to give essentially two different proofs of this, of both of these statements. So one theorem is, one way is to sort of explicitly understand these polynomials. The second way is to understand it in terms of solvable groups and state the theorem that Galois in fact proved, which is a beautiful theorem, which says that a polynomial is solvable if and only if its Galois group is solvable. So that I will do separately. Okay, so let me first, today our goal is to prove the following theorem. If I don't finish it today, I will finish it next class. So in the next two classes, the goal is to prove the following theorem. So let f be a subfield of C and let f small f be a polynomial of degree less than or equal to 4. Okay, so then I want to show then f is solvable. Okay, so let me just do some easy cases first before I develop some theory that will be useful for us later. So first, degree f equal to 1, then f is of the form some x minus a. We can always multiply by a scalar with of course a in f, so f is obviously solvable. So I keep forgetting this, solvable over f, triviality, right? Degree f is 2, then f is some x square plus bx plus c, and this, of course, if f is irreducible, you have to construct a bigger field where it splits, but otherwise the roots are in capital F itself. But in either case, quadratic formula, I will simply write it like this, quadratic formula does the job, right? Because the roots are so of course they are contained in a field like this. So this is a degree 2 extension, at most a degree 2 extension. It could be degree 1 extension if the discriminant is already a square. Okay, so I want to highlight that here. This is f if is an f, or so let's say k is this, which is the splitting field. So k equal to f if this, otherwise it's a degree 2 extension. And in either case, the roots live in a radical extension, right? Because any degree 2 extension is radical. We don't even need to do that. We can also use the theorem that we proved in the last class, which I recalled at the beginning of today's class. We do have a cyclic extension which contains the fields, which contains the roots. So either way, it is another way of arguing this is cyclic. So that means roots are solvable, and hence f is. Degree f equal to 3, I want to spend some time, but I first want to claim that I have already done this. We already showed, okay, so let me set it up properly. So let's say K is the splitting field of f over capital F. So now we have a bunch of possibilities. So in this case, solvable. This is solvable, right? Because this can happen, for example, if your cubic polynomial is reducible and it factors as a irreducible quadratic and a linear polynomial. This can very well happen. So in that case, it's solvable. Remember that the splitting field degree divides 6, which is 3 factorial. Okay, so it's either 1, 2, 3 or 6. So in this case, K over F is cyclic. I mean, in fact, in both cases, 2 and 3, it is cyclic, and hence K over F is solvable. Because every alpha in K is in a cyclic extension. So if you go back to the theorem that I recalled at the beginning of today, apply the third or second or fourth, all of these will work. So there is a tower where each extension is abelian or cyclic of prime order. All these 3 conditions are satisfied. So everything in the end field is solvable. Here there is only one single extension. The tower consists of a single extension. And this is abelian or cyclic of in fact prime order. This is solvable. So every root is solvable. And finally the last option is, in this case we already showed as part of an exercise, okay, so this is degree 2 and this is degree 3. So if you remember, we proved this exercise. Any Galois extension of degree 6 is solvable, because you can take a subgroup of order 3, look at its fixed field, because that subgroup has index 2, it is normal, so this extension is Galois. So degree 2 Galois means it's cyclic, and this is degree 3 of course, so it is also Galois. So this is also fine. However, I want to do a little more analysis of degree 3. Okay, so now I will pause the proof and do some generalities. Pause the proof here for some general statements. I will come back to the proof in a few minutes, but let me make some general remarks. So as always, F is a subfield of C, small f is a polynomial over capital F, and degree F is at least is n, which is a positive integer, okay, some positive integer. So I want to first define, for simplicity, the Galois group. The terminology is that the Galois group of F is the Galois group of the splitting field. So again I should write here, Galois group of capital F, small f over capital F is Galois group of K over F, where K is the splitting field of small f over capital F. Okay, so first I claim that, so I make some remarks here. So let's say proposition. So the Galois group of F is certainly a subgroup of Sn. Okay, this is clear, right? This is easy. Because F is degree n, F has n roots. Maybe they are repeating because F could be reducible. Nevertheless, if it has roots alpha through alpha n, and so let's say G is the Galois group of F. And if sigma belongs to G, sigma permutes alpha 1 through alpha n. So there is a map from G to Sn, right? Take sigma and look at it as a permutation of 1 through alpha n. And if sigma fixes every alpha I, then sigma is identity on K, because remember K is F alpha 1 through alpha n. By definition, K is a splitting field of of small f over capital F. So it is generated by them. So that means this is an injective map. Injective group homomorphism, right? So that means G is isomorphic to a subgroup of Sn. It could be any subgroup a priori. Now let's say F is irreducible, implies, this is important for us. So this is sort of an important proposition. So F is irreducible implies G is isomorphic to a transitive subgroup of Sn. Okay, why is this? First of all, what does transitive mean? Transitive means given any two indices I, j in the set 1 through n, there exists sigma in G such that sigma I is equal to j. So it means the orbit of any root is the entire set of roots. So if you forget the roots and you just think of G as permuting indices 1 through n, given any two indices there is a group element which sends one to the other, because that means sigma, there is a sigma which sends 2 to 3, there is a sigma which sends 2 to 4 and so on. And why is this true? So let alpha 1 through alpha n be roots of F in K, which of course is F alpha 1 through alpha n. Then what is F alpha 1? This goes back to some of the earlier thing we did in the course. Because F is irreducible, we have this, but this is also same as F alpha 2. So there is a map like this which sends, which is identity on F and sends alpha 1 to alpha 2. So basically here alpha 1 goes to x bar, alpha 2 goes to x bar. So you compose these two to get this map. And then you can always extend this using our standard extension theorems. Extend this map. So sigma sends alpha 1 to alpha 2 and fixes F. That means sigma is in G, which is Galois group of K over F, and sigma alpha 1 equals alpha 2. So the upshot is, basically the upshot is, given any two roots of alpha 1 alpha 2, there exists sigma in G such that sigma alpha 1, or let me just say alpha I alpha j. Okay, this is a property of group, the field homomorphisms. You can interchange any two roots. And let me warn you that this is not true if F is not irreducible. For example, if you take x to be x minus 3 x square plus 1 in Qx. So the roots are 3i minus I. Right? So the Galois group of F, if I use this notation, is a subgroup of S3, but in fact it is S2. So if you call the roots, these roots alpha 1, alpha 2, alpha 3, the only things here are those. So G only contains the trivial identity homomorphism and the automorphism which sends 2 to 3 and 3 to 2. In fact, G is equal to that. So G is not transitive. Talking about roots, G has no permutation which sends 3 to I, for example, because 3 and I have different irreducible polynomials. So it's not transitive. However, if f is, let's say, x cubed minus 2, then G is a transitive subgroup of, here roots are cube root of 2, cube root of 2 omega, cube root of 2 omega square. So in fact, G is equal to S3 in this case. Okay, so irreducibility is important. So the proposition 2 says if f is irreducible, G is isomorphic to a transitive subgroup of Sn. And this sort of puts conditions on what possible Galois groups can occur. And so this is important for us to keep in mind. I will use this later on. Okay, so now let me continue with general remarks. I will go back to the general situation. So f is an arbitrary polynomial of degree n, and let's say alpha 1 through alpha n are roots of f. So capital K is always fixed to be the fixed field of small f, and the roots are alpha 1 through alpha n. So the discriminant of f is defined to be, so discriminant of f, or D usually we will denote this, is simply the product of alpha I minus alpha j whole square, and we do this for every I less than j. For every pair of indices I less than j, we take alpha I minus alpha j. So the claim now is D is in f. So a priori it is in K, of course, because alpha I and alpha j are in K, alpha i's are all in K. So this is in K, but in fact it is in the base field. This is because let sigma be in the Galois group of K over f. Let's call that G. So then what is sigma of D? What is sigma of D? So I claim that sigma of D, since sigma permutes alpha I, so this is an easy exercise for you. This set I claim that sigma, so basically I want to claim this, so let me explain this. So here, for example, if n equal to 3, just as a simple example. So here we have alpha 1 minus alpha 3, or let's say alpha 2 first, alpha 1 minus alpha 3 square, and alpha 2 minus alpha 3 square. And now you take any sigma in G, it simply permutes the 3 roots. As an example, let's say alpha 1 goes to alpha 1, alpha 2 goes to alpha 3, alpha 3 goes to alpha 2. So here we have alpha 1 minus alpha 3 whole square. Sigma is an automorphism, so you can just apply inside the bracket. Alpha 1 goes to alpha 1, alpha 3 goes to alpha 2. Alpha 2 goes to alpha 3, and alpha 3 goes to alpha square, alpha 2. So remember, sigma of alpha 2 minus alpha 3 is alpha 3 minus alpha 2. However, once you square, so this is minus of alpha 2 minus alpha 3. So this is sort of a crucial observation. So alpha 2 minus alpha 3 goes to minus of alpha 2 minus alpha 3. But because D is squaring all these terms, you get no new element. Okay, so this I will leave as an exercise for you, the general proof. Essentially the same idea. So sigma of alpha I minus alpha j is some alpha of sigma I, thinking of sigma as a permutation. So you take the product, apply sigma inside the product, everything appears somewhere else, and because sigma is an automorphism of alpha I to alpha j, we are able to say that sigma of d is equal to d. But that means, so that part is an exercise. So this implies sigma d is equal to d. Okay, so this I will let you do that. So hence sigma of d equal to d for all sigma in G. So this implies d is inside k power G, which is in F, because k over F is Galois, because it is the splitting field of a polynomial and we are in characteristic 0. So d is in capital F. So that is a statement. And some facts that I will write here. For degree 2, you take F to be a degree 2 polynomial. What is the discriminant? You simply have alpha minus alpha 2 whole square, right? There is only one pair ij. And if you think about this, this is exactly the if you think about this, this is, if F is x square plus a1x plus a2, then you get this. Okay, so this, or rather maybe I'll just write it like this, x square plus bx plus c, then you get the usual discriminant that you are familiar with, because alpha 1 plus alpha 2, remember, is minus b, alpha 1 times alpha 2 is c. Okay, so use this to conclude this, because if you take alpha 1 minus alpha 2 square, this is, or alpha 1, yeah, so alpha 1, that will be alpha 1 plus alpha 2 whole square minus 4 alpha 1 alpha 2, right? Because you did, this is alpha 1 square plus alpha 2 square minus 2 alpha 1 alpha 2. Here you get plus 2 alpha 1 alpha 2, you subtract minus 4 alpha 1 alpha 2, you get the right thing. But this is b square minus 4c. Okay, that's all. So I have done the exercise for you. So this is our usual discriminant. But if n equal to 3, in which case let's say f equal to, so I'm going to write it like this. So f is x cubed plus a2x square plus a1x plus a0. Okay, then discriminant of f has a formula which is significantly more computation to do than the degree 2 case. However, you can do this, it's not completely impossible, but you can do this. So this is the fact that I will write, which in the examples I am going to use this occasionally. So this will happen to be minus 4 a2 cubed a0 plus a2 squared a1 square plus 18 a2 a1 a0 minus 4 a1 cubed minus 27 a0. Okay, so this is just a significantly messier formula, but it's irrelevant for the theory that we want to develop. So I just want to record it because in some examples I might want to mention this. Okay, in general, of course, in higher degrees the discriminant becomes significantly more complicated to write, and we don't care for a closed formula for it. But now let me make this third proposition which I want to do. So let f be a subfield of C as always. F is a polynomial in the base field and degree f is n. Okay. Let D be the discriminant of f. And let delta be square root of d. Remember, square root of d is actually alpha product, alpha minus alpha j, I less than j. Discriminant is the product of the squares of the differences. Square root of the discriminant is just product of the differences. This is of course in k. Okay. Now I claim that whether it is, so d is delta square, whether delta is in k or f or not determines something about the Galois group. So then the first statement is, if delta is in k, or rather delta is in f, that is D is a square in F, right? That means D has a square root on F. Then G is contained in AN. AN is the alternating group. That means it's a subgroup of Sn consisting of even permutations. If delta is not in F, that is D is not a square F, then of course G is not contained in AN. Okay, so the proof is so recall AN equals even permutations. In Sn, right? So this is a normal subgroup of index 2. So the order of Sn is n factorial, and there are exactly half of them which are even. Okay, so this is just to recall for you. Okay, so now note the following: G is not in AN. This is if and only if G contains an odd permutation. So of course remember G, which is the Galois group, I should have mentioned that G is the Galois group of F, which is the Galois group of the splitting field of K of F over F. Okay, that G contains an odd permutation is the statement that G is not in AN, right? If it is in AN, it cannot contain an odd permutation. If it is not, and if it contains in an odd permutation, if it is not contained in AN, it means it contains an odd permutation. This is just a definition of not being in AN. Now that means I claim now sigma delta is equal to minus delta. So this point is related to this proof that I asked you to do, because if sigma is an odd permutation, so let's say sigma is n is odd, then that means it interchanges. You can argue like this. I mean, so it okay, so it can be written as a product of, okay, so maybe sigma can be written as a product of an odd number of two cycles or transpositions. Okay, now let's say 5 transpositions. Now let's go back to delta. Delta is right here, right? So if sigma can be written as a product of 5 transpositions, all 5 of those will interchange alpha I and alpha j. So the sign of alpha I minus alpha j changes. So there will be 5 sign changes. Altogether they will give a minus sign. So that means sigma of delta is minus delta. So if sigma is odd, this happens. Okay, this basically if and only if, because if sigma is even, that means it can be written as a product of an even number of transpositions or 2 cycles, then there will be an even number of sign changes and they cancel each other and delta is fixed by sigma. So sigma delta is minus delta if and only if it is odd. That means delta is not in, of course, because we are in characteristic 0, minus delta is not delta. So sigma is not in Kg, that means it's not in F. So, okay, so this is a bit confusing, but what I'm saying is that for a fixed delta in Sn, if it's not in F, that means sigma some sigma doesn't fix delta, but that whatever that doesn't fix delta must be odd. So basically the exercise that I want to do is, given sigma in G, either sigma of delta is delta or sigma of delta is minus delta. and this happens only if and only if delta is even. This happens only if and only if this is odd. Okay, so this is the exercise which essentially sort of is proved here, but I want you to spend some time to think about this and make sure that you understand. This is a crucial observation about Galois groups of polynomials. The image of the square root of the discriminant under a Galois group element is either always that itself or its minus. So if it is not in, if it is in the fixed field, that means everything in G fixes it. That means only things in G are even permutations. That means G is in Sn. If it is not in F, that means something in the group element, something in the group does not fix it, but that means something in the group is not odd, sorry, not even. That means something in the group is even. That means G is not contained in An. Okay, so this, I went over this somewhat fast, but hopefully this makes sense to you. So please make sure that you sort of understand what I have done here. Whether the Galois group is in the alternating group or not is deducible from the square root of the discriminant. Now returning to the proof of the theorem. So the pause that I said earlier, now we are going to return to the proof of the theorem, which is that any degree 4, 3, 2, 1 polynomials are solvable. And let's first look at degree f equal to 3. So assume that 1 and 2 I have done. So I am going to safely assume that f is irreducible, because if it is not irreducible, it is a product of a linear polynomial and a quadratic polynomial, and each of them individually are solvable, so f is. So I might as well consider irreducible degree 3 polynomial. Then the Galois group of f is a transitive subgroup of S3, right? Because f is irreducible, by the proposition 2, its Galois group is a transitive subgroup of S3. There are only two such things. Namely S3, which consists of all of them, or A3, which consists of the 3 cycles. Right? Because other subgroups of S3 are the order 2 subgroups, and none of them is transitive, because, for example, if you take this doesn't send 1 to 3, right? So this cannot be transitive. So there are only two possibilities for the Galois group of an irreducible cubic. It's either S3 or A3. And the differentiating feature of these two is, in one case you have odd permutations, in the other case you don't have odd permutation. So let me just summarize what I have for degree 3. F as above, so that means irreducible degree 3. Then delta is square root of d. Then the first part is delta is in F if and only if Galois group is A3, right? And of course in that case k colon g is 3. In the second case, delta is not in F, that means g is equal to S3, and in that case k colon g is 6. Okay, so these are the two features of the Galois, two cases for the Galois group of an irreducible polynomial. So let me quickly give you a couple of examples covering both cases. So let's say f is x cubed minus 3x plus 1. Okay, so then as an exercise, use Eisenstein after substituting x minus 1 for x. Of course, you can't apply Eisenstein right away, so you have to change the variable to conclude f is irreducible. Okay, so that I will let you do this. So of course it is in the rational polynomial ring. Okay, so this is an irreducible polynomial. So what is the discriminant of this? So this is more or less the only place I will use the formula that I wrote earlier. Very messy formula, but you can compute it, and I will simply say that it is equal to this. Okay, so I simply say that use the formula. There is not much theory here. Okay, so this is not just it's just a computation. So this is not a square in Q. Of course, it's not a square in Q. For one thing, it's a negative number. So hence, K colon F is 3, the Galois group and is A3. Okay, so some calculations of the discriminant tell you immediately what it happens. So in the other case, you get x cube plus 3x plus 1 plus 3x plus 1. So again, this is irreducible. Use the same, I think, change of variable and use Eisenstein. In this case, discriminant of f turns out to be 3 power 4 is a square in, I'm sorry, so I think I wrote something wrong here. So this is 3 power 4, I'm sorry, is a square. Yeah, sorry about that. So x cube minus 3x plus 1 is 3 power 4. I don't want to do the calculation in the video. It's a waste of time because you can use the formula here, right? So just apply the formula and you make sure that I did everything correctly here. So here is a square, so the Galois group is A3. And in this case, it is the other one. So minus 5 times 3 cubed is not a square. So K colon F is 6 and Galois group is S3. Okay. So in this case, you have a degree 6 extension with Galois group 6 S3. Here you have a Galois degree 3 extension with Galois group A3, which is of course isomorphic to Z mod 3Z. Okay. So now also I think this is a polynomial that I said earlier has 3 real roots. One can check its graph looks like this. Okay. So just to remind you that that is the polynomial that we considered earlier. Okay. Okay. So now that leaves for me to prove the theorem in the degree 4 case. Next. Okay, let me stop the class here. I will do degree 4 in the next class, and that finishes the proof of the theorem which says that any polynomial of degree less than or equal to 4 is solvable over the base field capital F. Thank you.